Okay, let's get going. So I'm really delighted to welcome our CAIS Talk summer speaker today, Aaron Hertzmann, who's a principal scientist in research in California, also an affiliate faculty at the University of Washington. Did his PhD in computer science at NYU, and was, many of you know, a professor of computer science at the University of Toronto for many years, where I first met him, but then moved to Adobe Research. He's very widely published and widely cited, particularly in computer graphics and aspects of AI, but I think also in areas of overlapping art and human perception, which makes him, I think, an ideal speaker for the community here. He's received many awards for his work. I was particularly struck by the receipt of the 2024 SIGGRAPH Computer Graphics Achievement Award, which is kind of a lifetime achievement award. And as you know, SIGGRAPH is a very prestigious organization. So that's a great honor, I think. Anyway, without further ado, thank you.
Yeah, thanks for having me. So the work I'm going to talk about began several years ago or it was spurred by when I started to spend a lot of time drawing again, which I hadn't been doing for many years. I was doing a lot of sketching. And I would go out and draw a picture like this out in the world. And at the same time, I also like to take a photo together at the same time with the picture, just so later I have it for reference, when I use color, or just compare. And when I started, I often had this sort of gut reaction, which was, my drawing doesn't look like the photo, therefore I'm a bad artist. And I don't believe that, but it was sort of like my first impulse response. And that, but then I would do the thing of like, which maybe you've done, or if you haven't, you should, look at the picture on the screen and see how it compares with your visual experience of the world, and see, well, actually, they're really different from each other well. So the photo isn't capturing your experience very well. So that led me on this road to thinking about how is it that we should think about perspective, and how pictures depict our experience in the world, how they differ from visual experience. And it turns out that leads to thinking about how 3D vision works in the world as well, and what is visual experience. And specifically in this work, I'm focusing on projection, so the geometry of how 3D objects in the world project to 2D points in image planes. And the goal is roughly, that I want to study here is in human vision. When we look at pictures, what assumptions do we make about perspective? How does human vision, what is the constraints on how human vision interprets geometry? And I'll repeat this again in a moment. So in the space of projections, of course, the conventional wisdom, or the conventional theories around linear perspective, invented by Brunelleschi and written down and developed by Alberti. And the conventional Renaissance techniques are drawing rules, systems for how to draw pictures, placing one or more vanishing points and drawing a bunch of straight lines. And as a drawing technique, it was very popular in Renaissance as a way to make it easier to make pictures look real. So artists in the Renaissance had to learn the technique and learn how to use it to make nice looking pictures. This is an earlier example, which is a little bit like people are a bunch of billboards floating around in the Matrix on top of the grid. And as they got better at it, Rothbard's School of Athens is a really famous example of a very harmonious use of people integrated with linear perspective geometry. And now, as you know, of course, all of our cameras and mainstream computer graphics techniques rely on linear perspective, as you can tell from all the straight lines converging to vanishing points. But without, throughout prehistory and history, we have depicted things in so many other different ways. It's not just linear perspective, from ancient cave paintings lay out objects in space in a sort of free-form way, to ancient Chinese parallel projection techniques, through many other techniques in modern contemporary art, people depict space in lots of other different ways. And also, of course, with computational photography, so this panorama mode on the iPhone, there's lots of other ways to depict spaces besides just linear perspective. So, as a review, sure everyone knows, in linear perspective, you have an image plane and a center projection, and the way you determine the projection from 3D to 2D is to draw this line, intersect it with the plane, and that tells you where the 3D point has to project onto the image plane. And the idea behind this, or one motivation, is that if you were to transfer all the colors or reflected radiances of the world onto the picture plane by this rule, then you would when looking at the picture would be just like looking at a window into the world. So that's the idea behind that. So again, the goal here is to figure out what are the constraints on projection that human vision actually expects. So if human vision interpreted pictures according to linear perspective, then for any point on the image plane, the 3D point would have to be somewhere on the line to the center of projection. But it could be some other system. It could be that some other geometric constraints that vision obeys, and so the question is, what are those constraints? Now, as I've gotten into reading vision science literature over the past few years of reading it, the impression I got is that a large body of the work assumes linear perspective is the right thing in some way. The experiments and the writing sort of say human vision often misperceives linear correct perspective. Why is that? And yet, no one I've talked to actually seems to believe this. So, partly this is just me learning how to read the literature, but it's all the vast body of literature in some ways seems to assume linear perspective. And there's exceptions, including work of Jan Kunderich and Rob Pepperell, which I found very, very inspirational for what I'm going to talk about. So in order to motivate some of the things I'll talk about later, first I want to begin by discussing some of the limitations of linear perspective. Again, this is, I think, fairly well known. The most common, well-known one, which is known since the Renaissance, is wide-angle distortion. So the faces and the ball in the corner look stretched. And in order to, the conventional explanation for why they look stretched, people will say it's because you're not viewing from the center of projection. So then the question is, where is the center of projection for this picture? Anyone know? Anyone have an idea? This is with an ultra-wide smartphone photo. So I would not have been able to answer this before I started reading about it. So basically, to be from the center of projection, you need to be 2/5 the image width. So on this screen here, your eye should be where my thumb is roughly. And if your eye is not there, then you're viewing the image incorrectly, according to the conventional theory. So wide angle in this context means that the viewing angle from the center of projection is much wider than from the normal viewing distance that you would view it at as now. And indeed, if you move the eye, the camera center to the center projection, then the distortion in the corner does go away. But there's a caveat here that it only works with monocular vision. When I did this with my own computer monitor with both eyes open, then I see the distortion. And that's actually what Dhanraj Vishwanath and Marty Banks reported in their paper on this as well, or they predicted it at least. So we really view pictures from focal centers. Even when they have focal centers, we see big faces on giant billboards and huge landscapes on our little phones. So that's not really how we view pictures. So it's not really accurate doesn't really explain what's going on. And indeed, even there's a wisdom that this is what artists should do or what they do. But Martin Kemp, the Oxford historian, did a survey of the Ashmolean collection of classical paintings, and he found that only 3% of the paintings actually follow the rules of linear perspective. And there's a caveat, this is like following the construction rules. But you look through so many great artists in history, from Leonardo da Vinci, Turner, Hockney, have written, their early writings say, perspective is the right thing to do, you should be viewing from the center of projection, and then later on they write, well actually it has all these problems, it doesn't look perceptually accurate and so on, they do very, very different things. And if we look at any classical examples, such as Raphael's School of Athens here, the architecture does follow one point linear perspective very well, but you look at the people in the corner, the spheres, the globes are circular, whereas in linear perspective they should be stretched if they were to be consistent with the architecture. But also the faces should also not stretch the way they should be. And in one paper they worked out what the stretch should be. It should be about 1.2 to 1, and so there should be a little bit of stretch there on all of the faces if this was really following linear perspective. And so the way Kemp describes it is that artists have used linear perspective as a working tool for making convincing results, not something you strictly follow. And I would go further, I would say that wide-angle paintings throughout our history, when they're realistic, are really multi-perspective. So it's not that there's one center projection for the whole picture, there's really separate centers of projection for different parts of the picture. And this is going to lead to many more ideas later. And so like, when you see some giant panorama here and all the faces are not stretched the way they would be, then this is really more like having separate perspectives for different people. Or even for non-linear perspective, or not linear perspective, it's the same idea for people. So within computational photography, there's a set of works that actually are techniques for making pictures that don't look distorted, that actually, in a sort of more generative way, illustrate this idea. So here's Fredo Duran's holiday card from a few years ago. And the way he made this was he photographed his family inside this cardboard box many, many times, and then he laboriously composited all the photos in Photoshop. And the main the observation here is it doesn't look distorted at all. Like, it doesn't look particularly funny or weird. The walls of the cardboard box maybe look a little triangular, but overall it's fine. And each copy here has its own vanishing point. This is an older photographer from many years ago who took these pictures in San Francisco, long before street view techniques. And the buildings look kind of trapezoidal. Each street has its own vanishing point, but it doesn't look distorted. It looks like the shape is a little off from the true shape. And this is a SIGGRAPH paper that automates that work. They take a whole bunch of photographs of the street scene, and then they automatically composite them into sequences of like linear projections. And again, it doesn't look very distorted. These are also horizontal composites of different perspectives, but it also works in depth. So this is a technique from a group at Santa Barbara in which they have essentially, you take a bunch of photos by a dolly zoom relationship so that the camera center is moving as well as zoom at the same time. And the photo on the right is essentially a composite where the people in the foreground have one camera center and zoom, and the mission in the background is a different one. And it looks, I think, perfectly plausible. One more fun example, this is an animator in Disney for a movie Encanto. They're working with linear projection camera systems in computer graphics, but to achieve this particular setup, the way he got it was by stretching the geometries. One other set of techniques which I think is worth knowing about in computer graphics is a single camera center warp, where you start with a super wide angle photo like this, and you just warp it. So it's still a single projection, a single center projection, but very nonlinearly warped so that all the different parts of it look plausible. And the reason to mention this, one reason is that there's a more automatic version which was developed at Google, and this runs in every Google Pixel smartphone. So if you Google Pixel since version 3 or later, and you shoot in ultra-wide mode, then it does face detection in the corners of the picture, and replaces any face with stereographic projection, which means that, as you can see here, all the straight lines around the face are getting bent, but the face doesn't look distorted. And feel free to, by the way, interrupt if you have any questions or comments along the way. Okay, so that's a bunch of techniques, and now I want to start to begin to build up some explanation, descriptions of when things look distorted and when they do not. So I'm going to present a sequence of hypotheses, and they're going to get more and more sort of generic. And the first one, this is maybe more of an observation, that once you have recognized an object in the picture, then the shape you perceive of that object doesn't change when you see the rest of the picture. It doesn't depend on the context. So for example, with the car here, you have a sense of the shape of the car. If you crop it out, that shape perception doesn't change, or completely change the surrounding picture, again, the perception of the car's shape doesn't change. This is just about the interior shape, like normals and geometry. So it's not about, the relationships obviously do depend on the context. So at least the shapes of these two, this person looks the same as that one in terms of shape, but the relationship and size does depend on context. And it also, like I mentioned, it depends on recognition. So if you see a person running away from you or a dog running towards you, it produces a different shape perception. And that can depend on context. Okay, so shape doesn't depend on the rest of the picture. And so that, I think, implies that shape perception cannot be based on global camera estimation. Because if this means that you can't be inferring the center projection for a whole picture, like linear perspective, or inferring stereographic projection parameters or anything. This means that shape perception has to be a local property, not one that depends on inferring projection models. Okay, so when do things look distorted? And when by distortion I mean things don't look right. So sometimes people use distortion to refer to optical distortion, not being linear, and I don't know often that's what that means. But here we're referring to, does it look right? Does it look distorted? It's about perception. And I claim that we have a sense of when things do look distorted, when they look right or not look right. That this, if you know what a basketball looks like, this doesn't look like a basketball shape. And we have a sense when you look at this, there's sort of two things going on. There's a duality between the depicted shape and your knowledge of what the actual shape must have been. And we, with this duality, knowing the conflict or the disagreement between the depicted shape and the actual, what the shape must be, it creates an interesting tension. Okay, so one observation that, yes?
We defer this for later, but I'm just trying to, that hypothesis one is really interesting and very strong. So I'm, of course, busily trying to come up with counterexamples. And so how does this relate to like an ellipse? You just see an ellipse.
Yeah, so if you just see an ellipse, then, so this is all about your knowledge of what the shape should look like.
Yeah.
So if you saw like an elliptical object, and you don't know anything about what shape, I assume you would just perceive it as an ellipsoidal object.
Yeah.
If you saw, well, a 2D drawing of an ellipse, that's not really depicted in 3D necessarily. So,
but if you now see a field of ellipses and there's like a boundary frame from your perspective, aren't you now going to maybe see those as circles?
sorry?
If you now place that ellipse into a field of ellipses, and you now linear perspective, let's say on the frame, when you now see perhaps that ellipse as a circle. So like it's the context.
So like, do you mean like the
shape.
ellipsoid here?
Well, these are not ellipsoids. I'm just dealing with a simple 2D ellipse. So the hypothesis one is that shape is invariant to the context, right?
Once you recognize it, like if the context helps you recognize this is a basketball, then that's the one way it would not be invariant.
Yeah. So the example I was giving is how something that's elliptical in the image will be interpreted as a circle if you see it as projecting, so not changing its shape, but changing its attitude in 3D.
So like if you saw a tilted plane that had an ellipse drawn in it?
Yeah.
Yeah, then I think you would interpret it as
Circle.
well, I'm not sure you could recognize that it would be, I think you would recognize it as being foreshortened, and that the true shape must be less foreshortened than an ellipsoid, and possibly a circle.
So isn't that an example of context?
Well, then the interpretation, the 3D shape interpretation is a foreshortened little surface with an ellipsoid. So it's not, so the distortion is coming for foreshortening, not for projection. And I think that would be correct. I don't know, maybe we have to take it through and apply that. Okay, so one observation then, so when do things look distorted or not distorted? So one observation is that things never look distorted near the center of a linear perspective projection with a reasonable focal length. So, in the sort of the center, like say 1/3 of the picture, nothing looks distorted. And so this leads to the second hypothesis, which is based on a SIGGRAPH paper from 1995, but called the direct view condition. And the way that I pose it is as follows. If you pick any region of the picture, that looks undistorted if it looks like it contains a normal familiar object or an undistorted object, or a normal object as it would appear at the center of a normal linear perspective picture. So, for example, a sphere at or near the center of a linear perspective picture always projects to a circle. So whenever your spheres look like circles, no matter what the rest of the picture looks like, that will not look distorted. If it doesn't look like a circle, then it looks distorted. So that basically predicts a bunch of these familiar rules. Spheres should project to circles, straight lines should project to straight lines, and so on. And it doesn't works for any projection. Likewise, if there's some kind of warp, that predicts that these are distorted looking. Here, there's a very non-linear multi-perspective projection, but every part of it, every region looks undistorted because each region actually does come from the center of a linear perspective projection. Or in this non-linear projection, the Eiffel Tower individually does not look distorted because its region looks like a reasonable depiction of the Eiffel Tower. In this parallel projection, the people individually look like they could be linear perspective projections, and so they don't look distorted. This corner here isn't quite what you could possibly, you can't quite get that relationship in linear perspective, so it looks a little bit off. It's sort of a slight distortion. And there's more, maybe ambiguous cases you might perceive as someone with a really stretched head or as a distorted caricature of a real normal person. So we did one experiment based on these predictions. So we took, we generated a city scene and we projected with a wide angle linear perspective. That's this one, and this big volleyball in the right corner there. And we also made a version of that where the volleyball projected with a local linear perspective projection. And we asked people which one looks more like a volleyball. And if it were the case that people were inverting linear perspective, then they should prefer the one on the left, but obviously they preferred the one on the right. And we tried this with a few different perspectives.
So this is with the eye at the center projection?
I think it was at normal viewing distance, so not so definitely far back from the normal center projection. We tried this with other projection techniques as well. Now, with parallel projection, actually, people say that they slightly prefer the parallel projection, but these are cases where both volleyballs project to circles, so the hypothesis predicts that they're sort of indistinguishable. And in fact, the degree to which people prefer the local linear versus the nonlinear projection, or the other projection, is sort of proportional to the degree of stretch of the volleyball. So the more circulated, the more they say that it looks distorted. And just as an aside, we have
Don't you require to know where the person is relative to the picture? Because if you're really close, then that top one would look like a circle.
That's right. Yeah.
And
yeah.
So it depends, and that's not one of your variables. You've always got them at the same distance.
Yeah. Yeah. And so this is really about normal viewing. This is about normal viewing and regions in any kind of picture. So it's not about that particular special case. And just an aside, we have a paper coming up at a computer vision conference in CPR where we have a tool for just correcting distortion, where you, in this case, you sort of mark out the building on the right and say, I want that one to not be distorted, and then we apply a local linear perspective projection that, a bunch of other annotations, the rest of the picture, and then we can create these wide angle views for generic objects. The previous methods don't work for generic objects. Or for here, the image on the left, the marginal distortion adds a few pounds to the guy on the left, and so our method can take it off. I would argue that this hypothesis describes a phenomenon well across all sorts of different projection techniques and different approaches to photography, when things look distorted, when they don't look distorted. So why would that be? So now I'm describing so far I've described when things look distorted, but now I want to talk about why does vision work that way. And to do this, I want to step into 3D and talk a little bit about real-world 3D vision. There's a lot of results that I find very interesting and surprising. Maybe some of these are familiar to you, or maybe you know all of them, but I think it's worth looking at them because they're really unexpected. So the first thing I want to do is have you look at this picture for a bit. Maybe you know this demonstration already, but if not, just take some time to look and see if you find anything that's sort of non-photographic in here, not out of the ordinary for a photo. So that was a video. This is made by Michael A. Cohen. And so the main thing here is almost everything in the video is changing. And the reason I show this is to point out that when you know it's changing, when you look at something that is changing, you can see that change. I should set this demo so I can point to a specific change, but if you're looking in the right spot where something's changing, at the time it's changing, you can see it. In peripheral vision, you don't see it. So I take this as a demonstration of foveal versus peripheral vision. And now that I'm spending a lot of time thinking about this, I have this experience all the time. Like, I was walking down my street one day near my house, and I noticed there's a dry cleaner there, and I think maybe they had repainted or something, but I was like, how long has this dry cleaner been there? And I looked it up, and they've been there for like 15 years or 20 years. And then I start now looking around the house and say, I've never noticed that there. There's a little bit of paint in the floor here, there's all these things around us that we don't attend to, that we don't fixate on, and we're just totally unaware of, and we're unaware that we're unaware of them. On my iPhone home screen, at some point, as I was starting to think about this, I noticed that the second hand on the clock app is moving, which you should be able to see if you look right at the clock. And then I looked it up. How long has that been moving? It's like 13 years. So this is inattentional blindness or change blindness, depending on which version we're talking about. And so, and the argument that I'm very inspired by and influenced by Ruth Rosenholz's work, and she argues that a lot of this is really a function of foveal and peripheral vision. So what does that mean? So as you probably know, foveal vision is about 1.7 degrees or 5, depending on the definition of fovea. So the rule of thumb is you hold up your thumb at arm's length, and your thumb, the visual angle of your thumb is basically the visual angle of your fovea. So when I stood here, when I took this picture near my house, there's street signs over here, and I can see them just looking at them. But if you, I want to try this, fixate on one street sign and try to read the text on any other street sign. And I don't think you can do it. And it's sort of a little bit unexpected. It's really, like, you really have to be looking right at a piece of text to be able to read it, with exceptions. So much of our awareness is really in foveal vision. One more demonstration, this one's for Ruth and her colleagues. So stare at the red circle, and it's going to move. So now when the red circle moves, follow it with your eye. Okay, now feel free to move your eyes however you want, and it's the video is just looping now. Again, you know, there's so much. We're not only are we unaware of we're unaware of stuff. We're unaware of all the stuff happening in peripheral vision. We're unaware that we're unaware of it. So it's really getting less from peripheral vision, and so it seems like we feel like we are getting. So she describes this as kind of an illusion of awareness, that we're just unaware of how much we miss in peripheral vision. So, okay, so that's one topic. Now, the other thing I want to talk about is 3D awareness. So we have this feeling that we're aware of the 3D world around us, like you're doing 3D scanning of the world as we walk through it. And there's a large body of work that illustrates this is not true. So in my favorite demonstration, which is the technique of redirected walking, which is developed in VR systems. And the idea is this is for the situation where you want to have the person wearing a VR headset walking around in a large VR environment, but they only have a small room in the real physical space to walk around in. And so what you do is you have the system subtly rotate the world a bunch of different times during the experience, and then they don't notice, they feel like they're walking in the big room when they're actually walking in a small room. And some of the recent techniques for this use eye fixations and saccades to do it. So in the one illustrated here, whenever you saccade, it might slightly rotate the whole world around you, and then by the time your eye arrives, the world has changed. So if it were the case that we mentally reconstruct the world around us, or have some consistent 3D detailed knowledge of the world, then this would be really jarring, but people don't notice it. The other version is that the world rotates when you blink. So you blink, and then the world has moved a little bit, and people don't notice. So it's clear that we're not densely solving 3D shape or some 3D world representation. So this is called fragmentary 3D vision. So there's a large body of studies, as I mentioned, that illustrates various kinds of inconsistencies. There's a review paper by Paul Linton that was my kind of exposure to all of this. The motivation for this is you don't need consistent representations to perform tasks. You just need representations that are good enough to achieve whatever task you want to achieve at the moment. Like if someone throws a ball for you to catch, you don't need to mentally reconstruct your whole path to where the ball is going to land. You probably can't. You just need to know which direction to run. The big question across a lot of this work is, in what way is it fragmentary? So is it fragment, Danosh Vishwanath has a paper arguing that it's fragmentary across different distances, reachable versus not reachable. Other people, Kundring has some claims about fragmentary across different objects. And I want to, I think these are all plausible. Here I want to make the case that vision is fragmentary across eye fixations. And so basically at every instant, when you look into the world, you get whatever you're looking at any given time, you have a very detailed, rich sense of shapes and colors and objects and so on, particularly foveal vision. Then when you move your eyes or blink or look away, most of that information is discarded. And only some high-level abstraction persists over time across fixations. So if you look at a tree, for example, you can easily, or look at the picture of a tree, by looking at it, you can easily count all the leaves. But if you look away or close your eyes, you would have no idea how many leaves there are, or you have an idea, but you definitely can't count them. When you look away, there's some kind of more abstracted representation of the brain that we don't really know what that is, but it's definitely not at the 3D scene level, 3D detail level. Okay, so with all that background then, I want to argue how that relates to 3D picture perception. So clearly, all these same phenomena, I think, happen with pictures. So in this example, there are two concentric rings, but as you fixate your eyes around it, the part you're looking at, clearly the rings are separated. In peripheral vision, they look entangled. But the key thing to notice is, no matter how much time you spend looking at it, the illusion persists. So if it were the case that you were like mentally reconstructing the picture in your head and then understanding your mental picture, then the illusion should go away. But it's like every single fixation is a new experience. So clearly, unlike a computer vision system, the pictures doesn't live in your head. The brain does not load pictures in the head and run transformers on the whole thing, contents or whatever. It's really fixation by fixation processing that happens. And so really, the experience is much more like you fixate on one person, one part of the picture, you get detail there, and then you fixate somewhere else, then you have a sequence of information, and you build up over time an awareness of the contents, but not you don't save the pixels. And this is why illusory pictures impossible pictures can be interesting, because you can keep fixating different parts, and it all looks like it should have, but it never does. Whereas if it would all fit in one fixation, it's a lot less interesting. And of course, it can get more and more complicated. So to sort of test this idea that it's, we did a change lines experiment. We have people with eye tracking. So we have people fixate on the center of the picture, and then we tell them to move their eye to the upper right corner of the picture, and we blank the screen when they saccade. And so when they get there, the projection for the object in the upper right has changed, and we ask them, did the picture change at all? And most people don't notice the change. So this suggests that when they're fixating on the center, they're not noticing the projection, or they're not noticing enough of the shape to remember it when they see the new projection in the upper right. And we did this with all four corners of the picture. So there's a version with the bus, undistorted, and so on. And then so after running all these experiments, we showed them a few different pictures and asked them, did you see any of these pictures? Which of these pictures did you see at any time during all of these trials? The picture on the left is one that we did show them, and they said they didn't see it. And the picture on the right is one that we didn't show them, and they said that they did see it. And the reason is that the one on the left shows distorted objects that they never fixated on at any time, whereas the one on the right shows all the undistorted objects in the corners that at different times they had fixated on. So it really suggests that picture viewing is more like the sequence of individual experiences that we piece together, and not like pixels that we piece together into a single picture. So what this, I think, offers one answer to the question of why it is that flat 2D pictures can convey such a compelling illusion of 3D, and that's because our 3D experience is a lot less than we think it is. It's really a bunch of, one fixation experience and not a complete 3D scan. Okay, so now, how does perspective work? How do we perceive shape? So this is a figure from a nice paper by these people, Hendrik et al. And so the question I have is, how are the people facing with respect to each other? Are they facing parallel? Are they facing away from each other, facing towards each other? It's a wide-angle linear perspective projection. And usually people can figure this out, but no pressure.
What was the question?
How are they facing with respect to each other? Parallel, yeah, right. Yeah. So these people are facing parallel to each other, but the picture gives the impression that they're facing away from each other. So Jan on the right there looks like he's facing to the right. And if you crop the picture, again, that sense doesn't change. So it's not dependent on where we are in the picture that what his orientation looks like. So the final, most general version of the hypothesis I'm calling fixation-centered perspective. And the idea is that in each eye fixation, the picture shape is interpreted in terms of linear perspective centered on the eye fixation. So when you fixate on Jan on the right here, you interpret this as a local linear perspective picture, mostly emphasizing the area around the fixation. Then when you saccade somewhere else, then we have a new projection centered on this new fixation. And I'd further argue, for reasons we can discuss if you want, that we're interpreting it as the eye fixation being in front, the center projection being in front of the eye fixation. So you compensate for the surface slant from the viewing position. And we have an experiment about that, which I won't go over unless people are interested. So to summarize these hypotheses, these are all hypotheses about local shape. I'm not saying anything about overall 3D awareness. The first is that our vision in 3D awareness, the 3D world is fragmentary across eye fixations and also very limited by peripheral vision. Shape within a single region of picture doesn't depend on the rest of the picture apart from recognition. And in particular, we perceive shapes as distorted if they don't look like they could have come from a local linear perspective projection, and that because we interpret shape as if each region as though it has its own local linear perspective projection. Now, I claim that these hypotheses are consistent with lots of evidence. They're consistent with the limitations of peripheral vision and the nature of foveal vision. They explain why linear perspective has been such an effective projection technique throughout history, but also why it creates distortions and when, as well as the distortions created by other projection techniques, as well as including within art and art history. It describes paintings as being multi-perspective and why that works, as well as all these techniques that are used in computational photography and computational projections, as well as the results of the experiments that I showed. And I don't know of any other theory that has even attempted to even mention many of these different things. So again, this is all about local shape in pictures. What 3D do we preserve? 3D awareness do we preserve in time? And this is like, I don't think there's much work on this. No one knows. I certainly don't know. I certainly feel like we have a sense of, from both these pictures, you have a sense of arrangement of left, things are to the left or the right. Sometimes you get more of a sense of spatial awareness of in front of or in back. And it clearly can't be dense 3D, but beyond that, we really don't know much more than that. Okay, so this is all mostly about perception, but I think it also has implications for how we make pictures. and often I think about the process of making a picture is a little bit like a collage. So if you draw a picture, then a little bit, it's like you cut out pieces of pictures from a magazine, you can arrange, you pick how you want to depict all the individual elements, and you can also arrange them, and their arrangement will imply their relationships and spatial relationships and relative size, independently of sort of their shape or appearance. And in a sense, a lot of making a picture is about piecing together these local appearances to make an overall composition as sort of two separate phenomena. And when I draw pictures now, I often think of things this way. So like, so here's one. So I sat in a cafe and sketched and took a photo and later compared them. And there's a lot of common themes here that I noticed both in my own drawings and I can see in art history. So the street seems to have a separate linear perspective from the foreground elements. In the way that I drew this, lots of things are left out. I probably didn't fixate on them. And it's much more like piecing together different parts and different projections rather than a single global shared projection. And even when sometimes I do take a photograph and then draw a picture, using hours later using the photograph as reference. But now I often think about, well, like I want to, for the composition, I want to rearrange things and make it bigger. And I know that when I stood at that spot, the building at a different distance would have felt much bigger in real life than it does in the wide angle photo. And so, like I have that knowledge when I draw a picture to use as I wish. I know that the photo is not like objectively geometrically correct. So to summarize,
Can I have a question?
yes.
Have you tried like the new tools for image generation for kind of like ChatGPT and Midjourney and stuff to see to what extent they obey or not obey to the same rules of linear perspective and maybe try to understand from there what is going on? Whether like my assumption obviously is that they would obey, right? The hypothesis that you lay out here, and the question is, how can we know how LLM embed those hypotheses into the system as well?
Yeah, I haven't studied that much. There's a paper from UIUC where they write, I forget which image generation system they're using, but they say generation systems don't correctly follow linear perspective, and so they add loss functions to guarantee that all lines be at vanishing points. Beyond that, I don't, and there's certainly lots of things that they do. Actually, let's see if I have this slide. there's a lot that they clearly do that is not, it feels like they're composing things in ways that is not guaranteed to be perspective. Here we go. So, like this, whatever was going on here, this is a control net picture. There's no underlying 3D reasoning here or perspective reasoning going on. Things like there's some reasoning in the sense of like spatial arrangement and things that are closer or larger and stuff like that. But I don't think there's any meaningful 3D. You could build a 3D scene that satisfies that, but it's not really about geometric accuracy. Beyond that, I haven't really studied it. All right, almost back. So just to summarize the topic of perspective, get back to the summary slide here. So I argue we perceive shape in each eye fixation according to local linear perspective, and then this explains shape and perception techniques in art history and photography, and making a picture involves arranging and depicting these elements in space. And there's clearly like, almost everything I've said here is like, if you have a detailed question, I probably don't have an answer. There's many things to study, like, how much shape do we have in peripheral vision? How much information do we preserve in 3D? And almost anything else is an open topic for investigation. Many studies one could run here. I just want to briefly mention that my current project is a much more ambitious goal, not just understanding perspective in 500 years of art history, but also pictures as well. So we know that if you find, people have done a bunch of cross-cultural studies where they show somebody a line drawing or a photo when that person has never seen a picture before, and they can recognize these things. So we know that understanding pictures, at least certain kinds of pictures, is a product of real-world vision. It doesn't require learning. There's other examples with line drawings from that happening at the beginning. Likewise, I did one study, which I presented last time. I did a virtual talk at York, where I took a depth estimation model from computer vision that had only been trained on real-world imagery in depth pairs, and then apply it to line drawings, and it does a reasonable job of estimating depth in line drawings. So this implies that understanding photographs, including black and white photographs and line drawings, is not a learned skill. You can learn to get better at it, but it is a consequence of real-world vision.
There is also evidence from kids with cataract that were born blind, where they had surgery at the age of 13, that they are also process depth form drawings just after the surgery.
Is that John Kennedy's work?
No, Gandhi, I think, is the first author from machine biology. So they are susceptible to the Crohn's lesion right after the surgery, which is kind of
that's interesting. So the work I presented previously at York argues that the reason line drawing works as a consequence of real-world vision is that if you can recognize sculptures that could have occurred in the real world, and the line drawing, if there exists a real-world sculpture that looks like the line drawing, then the same visual processing that works in the right picture could work in the one on the left. And I'm not sure exactly what the real-world image might be, but if any of the first few pictures is something that real-world vision should be able to process, and the picture on the right looks enough like them that it should have the same visual features and the same visual processing should work for it. Now, let's deal with many other depiction techniques, and applying that same philosophy to a bunch of other different phenomena, which I'm happy to talk about later, such as tone mapping. The brightness of the sun here does not look like the real sun because it's not burning your eyes. So all photos we have are tone mapped through some nonlinear processing, whether from film or smartphones. And I have explanations for why we understand the pictures anyways. And again, happy to talk about this more later on. So all the papers that I talk about perspective are all at this link. Thank you very much.
Thanks, Graham. We could kick off, I guess. Great talk, very interesting. So, I guess it feels like there's a couple things going on. So you're really focused on narrow field picture perception, right? So like in the Kundering example, so you have this idea that it's multi-perspective. That's our natural way we record and remember. And so if we do multi-perspective pictures, it matches kind of our memories. But in that case, it's also rational, right? If I see a 5-degree picture of the size, then they are turned away from each other, right?
Yes.
So I think it's really interested in both of those issues. Like, if you give me, if I'm at the center projection and I have like a 90-degree field of view or something, and you give me the multi-perspective view, so now the faces are aligned with the z-axis. Does it seem to proceed? So your hypothesis is that, does it seem distorted? So your hypothesis is, or your claim is that it will look perfectly correct, right?
Well, so this is, I'm primarily talking about normal viewing conditions in which you can, so the one paper which is really influential and key to this is the Vishwanath and Marty Banks paper from 2005 on why where they basically show that you do slant correction if you can perceive the picture plane. So if you're looking through people, or you don't have depth cues and so on, then you essentially don't slant correct. And if you can see it with binocular vision, then you do slant correct. So that basically, did that answer your question?
Okay, so if you could construct this so that I couldn't see the picture plane, then it would seem distorted if you did multi-perspective. So
yeah, so like when you wear a VR headset, the light rate, they're constructed, the optical systems are constructed so that the light that goes to each eye matches the way it would have been in the virtual scene. And you're not aware of any distortion. And I once tried with my Oculus Rift, do a screen capture from the game, like have like a circular object in the corner, so like I'm facing this way and I look down and it doesn't look distorted at all, and then I look at the screen capture from the Rift on the screen, it looks totally distorted.
Yeah. If I can just follow up with another question. So the multi-perspective idea seems like a very strong hypothesis, and it's been talked about by various people. But it seems like a really strong test would be if you monitored my fixations, and then you constructed a multi-perspective picture based upon my fixations. And then David did the same experiment. You constructed a multi-perspective image based on his fixations and asked me to judge which was better or which was, more like my memory or something like that.
What does it mean to construct a picture based on your fixations?
So you gave an example of the city scene, right, where you said, in the tool, I want this building to be undistorted, as though I was looking at it. And so, but I think your theory is that our memory of a scene is based upon a sequence of fixations, and so those are recorded with kind of no distortion, so to speak, near the center of each fixation. So is your prediction that that would be the right multi-perspective composite to use based upon my previous fixations of that scene? To kind of index into my...
I think there's a lot of different things going on there because I'm not really talking about long-term memory so much.
Okay. But even short.
I think, so you may not be aware of scene content that you hadn't fixated on, and then you don't necessarily care how it looks. And in that case, you want to have the things that so when you look at the picture later, and then you saw something that was in this hypothetical generation looked distorted, and you hadn't seen anything distorted before, then I think that would look off. Like if the picture, when you looked at it the first time, didn't appear to have any distortion, and then you look at a picture that has distortion, even if you had not fixated on that object before, I think you would notice that. Yeah, I think once we talk about like long-term memory, like does it look the same, then because there's like many confounding factors there.
Okay, but your idea is that picture perception is somehow related to
how we see scenes through a sequence of fixations.
Yes, yeah. I'm sort of talking about the individual fixations. When you look at fixated part, does it look distorted? What shape do you perceive there? And how you put that together into a larger scene awareness, like I haven't studied that. I think there's not a lot that we know. I mean, there's separate studies, so like, let's say, Bainbridge had these like studies of draw a picture that you saw 10 minutes ago, and people leave stuff out and put stuff in or hallucinate things that would have made sense but weren't actually there. And sort of that speaks to that, a little bit of that as well.
This is super cool, and it was funny because you had like the buildings pictures, and I was just like looking through the buildings through these frames and the different fixations. I guess I'm really compelled by the multi-perspective story, and I'm curious about the one slide which you passed over very quickly and maybe don't have much to say about, but the 3D. Once you have different perspectives, the question arises of how we combine or understand relationships between those perspectives so that we know spatial relations across those different perspectives. Now, I was curious just if you had any thoughts about different possible hypotheses about how we do that. Do you think we're keeping track of, in the background, the relationships between the fixations we're making? And I'm wondering with what fidelity you had the CAIS experiment that you mentioned a while back, saying like in VR you can sort of shift around people, how CAIS work with what actual image they're getting in ways that are totally kind of unrealistic, but people don't notice. So I'm just curious to what degree we're keeping track of different fixations in order to understand the relationships, the spatial relationships across perspectives.
Yeah, and I think the answer to all those questions is that I don't know. And most of this is not really studied. So you read the CAIS paper to see like how, I'm sure they measure thresholds on how much you rotate the world, people won't notice. Because they're actually building a VR system. With regard to what information we get, your guess is as good as mine. My guess is that we have some sense of, we have some abstract relationship. This person's to the left, that one, this person's in front of them. You make more fine-scale judgments by studying it, doing more cognition. But I think casual, like in a perspective photo, it feels like there's a lot of relations you are getting, a lot of relative sizes and stuff. But maybe it is just nothing more than left, right, up, down, relative size, and some qualitative sense. And then, and it feels like you have dense 3D because every part you look at looks very precisely, gives you very precise information about what's in that region. And then for thresholds of how much you can rotate and stuff, I don't know. And like that with that study, the change blind study we did, we did like the most simple version of it. And what are the thresholds? What are the cutoffs? How much can you change you would notice? Don't know. I hope someone will study this thing. Any other comments or questions?
Not a very well-formed question, but so there's a difference maybe between how we perceive images qualitatively and how we must perceive them if we need to act. And I was just wondering about first-person gaming. I'm not a gamer, but do you know much about that? So I imagine that often the eye is not at the center of projection. So I'm just curious if something you've thought about whether that affects people's accuracy.
I think gamers play a lot of there's actually the colleagues in the VR study also did some studies on perception in first-person shooter games, and that was like their reaction times for peripheral vision. I think you learned just like I think we can adapt to different projections to some extent, in the sense that or even in the real world, you put on a new pair of glasses and it feels weird for the first hour or whatever, and then it's normal. I think the similar thing happens with projections in games to some extent. The gamers often use a very wide field of view, so you can see a lot. But then as you rotate the camera, things shape appears to change because it's the distortion is different for different projections. So you have a sense of the world shifting a little bit, but you get used to it, I think. So it's still happening, but I think you learn to adapt to it.
Moon illusion. Have you thought about the moon illusion? tool?
I have, yes,
The
and
same as
we're
your
working on
building
that.
looking too big thing.
Yeah. So I've specifically thought in the context of photography. So I've had this experience lots of times where I hit this slide where I should keep this. Let's take a second to find the slide I want to show.
I believe it's in one of your blogs in the morning.
Yes. So this is, so as I took in San Francisco, this is a photo looking down the street towards City Hall. And City Hall is off the distance there. And you look at the photo, City Hall feels so big in the world, and it's infinitesimal in the photo. And so we have a project, we're trying to figure this out. And so I think it's clearly perspective distortion causes become small. So like in one of Marty's papers, I think one with Emily Cooper, they sort of describe this when you're viewing wide angle pictures from too far away, it creates a sort of depth stretching effect, that things that are far become very far. But the question is, why is it surprising? Because at least to me, that's the first part is what causes it geometrically, but the other is why is it so surprising? Because everything far away is being made small, but we only notice that this building that we're looking at is something that gets small. And so I think that has to do with foveal vision and fixations or over attention. That I'm looking at the building, and the visual angle of the building is tiny on the picture compared to the real world. So the picture on the right there, I zoomed in enough until the visual angle of the building in the picture is the same as what I saw in the real world. It's like one thumb width as I held the phone at this distance. So that's, and also I'll just say that we look through our history, there's many examples we can find where, here, this is Turner's view of Oxford High Street. And he has done the same thing where the photo makes Carfax Tower and the church spire in the middle look smaller in the photo than Turner drew them from his painting. And we have lots of other examples in our history. There's more I can say about that, but that's what I'm thinking about anyways.
But you're just restating it, aren't you, that when you look at the moon, you're misjudging its distance or something, and doesn't explain all the things you're saying. When you've got the building far away and it looks too small, and the moon looking too small, do you have an explanation for that, or is that just are you just acknowledging it?
No. So just to clarify, I should say, so the moon illusion often refers to the moon looks too small when you're looking at it in the real world. I'm just talking about how things look in pictures. So I'm talking about a slightly different version than what people normally mean by moon illusion. And I think this is an explanation. The geometry of projection, of wide angle projection, makes distant things look have a much smaller visual angle in the picture than they have in the real world. And we only notice the ones that we're fixating on. We don't care about other buildings that got too small as a result of that geometric projection.
So throughout the talk, you were sort of talking about multi-perspective, and you've also talked a bit about different projection systems, and maybe we can adapt to different projection systems. I was curious if you think it's part of our ordinary practice to not only adopt multiple perspectives, but adopt multiple projection systems within a given picture. There's like a characteristic of like Hokusai and a lot of paintings in Japan after these Dutch linear perspective manuscripts came in, as they started blending together like linear perspective and parallel projection systems in ways that seem kind of seamless actually, so that you're looking at one part of the picture and it's got a kind of parallel projection system, and you're looking at another part and it's in linear perspective and you don't quite notice until you look carefully. Is that compatible with the general picture?
That's a great example. And it's an interesting question, to what extent was Hokusai doing that consciously, or just sort of free form, or some combination, or like doing it and then thinking about it? Yeah. But yeah, those are already examples.
So a little question. The nifty 50mm full frame lens, is that perceived as correct because it matches our natural field of view?
Yeah, so, and this is the Vishwanath Banks paper from 2005. They essentially argued that the 50mm matches our normal viewing position, or is that, sorry, the Cooper Banks one? Anyways, yeah, Cooper Banks paper, they argue that because we're viewing it from roughly the correct, the normal viewing distance matches the center projection focal distance that the camera proves. Anything else? This is after 12 now.
Really interesting, yeah. Okay, thank you, Aaron. Good. So I guess the nifty 50 depends on, you know, how large you're going to be.